In this video, we are going to have the proof of this lemma, which states that let phi be a homomorphism of G onto G bar with kernel K. For H bar, a subgroup of G bar, let H be defined by H is equal to the set of all X in G for which the image of X and phi is a member of H bar. That is, all those X in G such that phi of X belongs to H bar. So if these are given, then what we need to prove is H is a subgroup of G and K is contained in H. The second one, if H bar is normal in G bar, then H is normal in G. The homomorphic image of a normal subgroup of a group G is a normal subgroup of G bar. From the first two, we are going to establish one-to-one mapping between the set of all subgroups of G bar onto the set of all subgroups of G which contain K. So what is given to prove this? What is given? First we will write let phi be a homomorphism of G onto G bar with kernel K and H bar be a subgroup of G bar. Now let H be defined by all those elements in G whose image under phi is a member of H bar. We shall name this as equation 1. So we are given phi from G to G bar to be an onto homomorphism with kernel K. This is kernel K. Now we first prove that H is a subgroup of G. To prove that H is a subgroup of G, we have to prove that H is non-empty and closure as well as inverse are there in H. So first, as H bar is a subgroup, see for the first part we are given H bar to be a subgroup. So as H bar is a subgroup, E bar, which is the image of E under phi, because phi is a homomorphism, will belong to H bar. E bar is definitely present in H bar because H bar is a subgroup. Identity element must be present. So whenever we have phi of E in H bar, when this criterion is satisfied by any element, that element has to be in H. So we conclude that E belongs to H. So that in turn shows that H is non-empty. So we have so this is, which implies that E is in H, that shows that H is non-empty. Now we'll consider two elements X, Y in H. So if X and Y are in H, by the definition of H, phi of X and phi of H should be there in H bar. But we know that H bar is a subgroup. So closure holds in H bar. So you have this. But because phi is a homomorphism, from this you have phi of xy belonging to H bar. So whenever phi of xy is in H bar, this xy should be there in H. So by this definition, our xy must be there in H. That proves the closure in H. And for the inverse, we'll consider an element x in H. If x is in H, by the definition of H, phi of x should be there in H bar. And because H bar is a subgroup, the inverse of this element should also be present in H bar. So you have this. But because phi is so homomorphism, phi of x, the whole inverse is phi of x inverse. And whenever phi of something is in H bar, that something should be there in H. That's by 1. So your x inverse is in H. So that proves that H is a subgroup of G. Next, we have to show that K is contained in H. And that's very simple because by the definition of kernel, it is all those elements in G whose image under phi is the identity element of the codomain. So that is for all those X in G for which phi of X is E bar. Now we'll consider some K in K. If you are able to show that this K is in H, then we have what is required. So if K is in K, then by the definition of K, phi of K should be E bar. So that shows that E bar being a member of H bar, this phi of K should be there in H bar. Whenever phi of K is in H bar, by the definition of H, this K must be there in H. So that is by 1, you have K belonging to H. So K belonging to K implies K is belonging to H. That means K must be contained in H. Now to prove the second one, H is a normal subgroup of G if H bar is a normal subgroup of G bar. First we show that whenever H bar is a subgroup, then H is subgroup. Now H bar is normal in G bar means H is normal in G. That is what we are trying to prove. So to prove that H is normal in G, we'll have to consider an element G in G and H in H and we have to show that GH G inverse belongs to H. We have to show that GH G inverse belongs to H. If we have to show that GH G inverse belongs to H, we have to show that phi of GH G inverse belongs to H bar. So how that is established? See, if G belongs to G, phi being a mapping from G to G bar, phi of G naturally should be present in G bar. Now, if H is in H, by the definition or by equation 1, we have to have phi of H in H bar. But H bar is given to be normal. H bar is normal in G bar. So, we have considered an element from G bar, which is phi of G. The inverse of that, phi of G, the whole inverse. And we have to consider this phi of H, because H bar is normal in G bar, means for any element in G bar and any element in H bar, we have to have this this product to be present in H bar. Now, because phi is a homomorphism, because your phi is a homomorphism, we'll have to have this implying phi of GH G inverse belonging to H bar. So, if this one belongs to, the whole lot belongs to H bar, means this one will be there in H by 1. So, by 1 we have this to be true. So, H is normal in G. So, first we established whenever H bar is subgroup in G bar, H is subgroup. The second, we proved that whenever H bar is normal in G bar, H is normal in G. Now, here we have the homomorphic image of a normal subgroup of a group G to be a normal subgroup of G bar. So, all these are true only if you are given phi to be an onto homomorphism from, of course, here we have considered G and G bar. So, let H be a normal subgroup of G and phi be a homomorphism of G onto G bar. Now, we will have to prove that the homomorphic image, namely phi of H, which will have elements, it is a set which consists of elements of this form, where H range over capital H. We shall name this as 2. We have to show that this is normal subgroup of G bar. So, to prove that this is normal in G bar, first of all, it is non-empty, and then it's a subgroup and normalcy condition. So, all these are to be established. Now, we have to show all this, that is phi of H is non-empty, and for any two elements, closure holds. For any two elements in phi of H, closure holds, and any element in phi of H has inverse. And whenever G bar is in G bar and A is in phi of H, G bar A, G bar inverse should be there in phi of H, for phi of H to be a normal subgroup of G bar. So, how that is established? Now, we are given, see, in this part we are given H to be normal subgroup. So, being a subgroup, E must be there in H. If E is in H, phi of E will be there in phi of H. So, that shows that phi of H, there is an element in phi of H, and therefore phi of H is non-empty. And for the second part, we shall consider A, B to be two elements in phi of H. So, that means A can be written as phi of X and B can be written as phi of Y, where X and Y are from H. Because these are considered in phi of H, we can write like this. Now, we will consider A into B, that is phi of X into phi of Y. So, that is phi of XY, because phi is a homomorphism. From here, we conclude that AB is a member of phi of H, because XY is in H. XY is in H. Whenever X and Y are in H, XY being H being a subgroup should be there in H. So, we have AB belonging to this. So, closure holds. Next, for any element inverse exists, we have to show. So, let A belong to phi of H, which means A can be written as phi of X, where X is in H. Now, if we consider the inverse, this is what we have, phi of X, the whole inverse. And because phi is a homomorphism, we can rewrite this as this. So, we have A inverse belonging to phi of H. Why? Because X is in H. When we have X to be in H, H being a subgroup, X inverse should be there in H. So, because X inverse is in H, A inverse should be there in phi of H. And for normalcy condition, we consider this G bar A, G bar inverse. Now, because phi is onto, we can rewrite this G bar as phi of G, where G belongs to, where is that G? G is in capital G. So this is because phi is given to be onto from G to G bar. So this is replaced, and A is being a member of phi of H, that is also replaced, and this inverse, because G bar is phi of G, you have this step. Now we have this as such, and because phi is homomorphism, this is rewritten in this way. Because GH G inverse, actually GX G inverse, GX G inverse is in H. Why is it so? Your X is in, this X is in H. Here your X is in H, and capital H is given to be normal in G, and your small g is also in capital, small g is in capital G, X is in H, so GX G inverse should be there in H. So because GX G inverse being a member of H, this has to be in phi of H. So that shows that phi of H is normal in G bar. Now we notice one more thing. So from here, if L is a subgroup, then phi of L, if we denote that as L bar, is a subgroup of G bar. So that is what homomorphic image is. Again, a subgroup. Normal subgroup itself we have established, so subgroup condition is definitely there. Now we will describe a collection. Let T be all those Y in G for which the image of Y under phi is L bar. Then we are going to prove that this T can only be L. So the reason is, if you consider a small L, see, first we will establish L contained in T, and then establish T contained in L, so that both together will give us T equals L. So you consider an element small n in capital L, which means phi of L will belong to phi of L, and that's taken as L bar. So you have, whenever phi of L is in L bar, we have to have this T. T is described in this way. So phi of anything belongs to L bar means that that one should be there in T. So you'll have to have this L to be there in T. You have considered L in L, that in turn implies phi of L belongs to phi of L, capital L, and that's nothing but L bar. So because phi of L belongs to L bar, your L should be there in T. So L is contained in T. L in L implies L in T, so L is contained in T. Now for the reverse part, we shall consider T in capital T. If T is in T, by the definition of T, it is phi of T in L bar. So that in turn implies phi of T equals phi of L, because L bar is phi of capital L. For some L in L, we can have this one to be true. And here, as we did in the previous cases, in the one-to-one case and all, we can post multiply both sides by phi of L, the whole inverse, and make use of the fact that phi is a homomorphism, so that you will get this step. So phi of TL inverse is E bar. So phi of something is E bar, means this something should be there in kernel. Because kernel is all those elements which are taken to the identity element. Now from here we have TL inverse belonging to L, because K is contained in L. We have K to be contained in L, so we'll have to have TL inverse belonging to L, which in turn implies that TL inverse, L and T belongs to L. This is simply because TL inverse, you can have it as, say, some L prime, and then post multiply both sides by L, you will get the right hand side to be a member of L. So you have your T belonging to L. T in T implies T in L. So T must be contained in L. So both together gives us that T is equal to L. Now we have in the fourth claim that there is a one-to-one mapping from the set of all subgroups of G bar onto the set of all subgroups of G which contain K. We shall denote by tau the subgroups of G which contain K, and tau prime to denote the subgroups of G bar. We'll consider a mapping theta, we'll consider a rule theta from tau to tau prime by theta of L equals L bar for every L in tau. What is L bar? It is phi of L, and now we have to, this one being defined by us, we have to show that this theta is well defined, and then only 1 to 1 or on to whatever it is. So by claim 3, theta is well defined. In claim 3, we had that given a subgroup of G, correspondingly I can find a subgroup in G bar. So in fact, even normal subgroup also means we can have that to be normal, but here it's enough we have only subgroup. So we have L to be subgroup, so the correspondingly I can have one L bar to be subgroup in this. So such a description is well defined, so we can simply conclude that theta is well defined. Now by claim 1 and note under claim 3, theta is onto. For onto, what does that mean require? If you consider any subgroup of G bar for which I should be able to find one subgroup in tau, so that the image of on that particular pre-image under theta should give back the original one from where that we started. So that is achieved from claim 3. What is claim 3? Claim 3 is, and this is note under claim 3. Claim 3 states that the homomorphic image, we don't as such here require normalcy. The homomorphic image of a subgroup of a group is a subgroup. So this is what we have, and we make use of that, and that is for theta well defined. So for onto, we'll have to go to claim 1 and note under claim 3. So here note, claim 1 is this, that is whenever I have a subgroup in the codomain, I can always find one H for that, which is defined in terms of this, then this H will be a subgroup. So for every element in this, I can find a subgroup in the domain. So that's what claim 1 says. And when I consider L bar, the pre-image cannot be something else, it will be L. So that is ensured from this note. So we conclude that from those two, that is by claim 1 and note under claim 3, theta is onto. Now to prove that theta is 1 to 1, we will assume the images to be equal and establish the pre-images are equal. So theta of L equals theta of M is assumed, that is L bar equal to M bar. Now we will prove that L is contained in M and M is contained in L, for which we will consider, so this is what we claim, L equals M means then we will have our theta to be 1 to 1. That's our aim. So we will consider one A in L. So phi of A will be in phi of L, which is L bar, but L bar equals M bar. So you have your phi of A belonging to M bar, but whenever I have phi of A in M bar, our A should be there in M. That is of the description or the relation between M and M bar that we have given. So you have your A to belong to M. Similarly, just retracing the steps, you get A in M implying A in L. So we have M contained in L. From this implication, we have L contained in M, and from this direction, if we go back, retrace, we get M contained in L. Those two together gives L equals M. So that shows that there is a one-to-one mapping from the set of all subgroups of G bar onto the set of all subgroups of G which contain K. Now in the next video, we'll see the second isomorphism theorem and third isomorphism theorem. Thank you.